is. Okay, good morning, ladies and gentlemen. So, oh, nice and green. So, again, before I start, let me see if you guys have any questions for me. I hope you do. Be a little bit more proactive, less shy. That's okay, I don't bite. If not, well, I guess a couple of things. First of all, spring break is next week. Yay. Then we have another week, and then we have a week with a midterm that's scheduled for April 8th, Tuesday. Same rules as before. So, you know, while you're somewhere on the beach in Miami or in Hawaii, you know, open a book, prepare for the midterm, for the impending doom about a week after you come back. So the midterm is about the same as the scale. Well, the format is the same as before. You'll have 20 multiple choice questions. You'll have 3 freestyle short answer questions, similar to the essays that you're writing, but maybe one paragraph of an essay. And it will cover chapters from 5 to 9. Although, depending on what happens when you come back, if you'll have a guest lecture on Tuesday of the week when you come back, I might include chapter 10, but probably not. So by default, it's chapters 5 to 9, and we'll talk about the global warming in the week after the midterm. So that's the announcement for the week after the midterm. One more thing. So we're going to be discussing light, electromagnetic waves, but in particular visible light this week, infrared, UV. After we come back from spring break, there are a lot of cool demos here. I'll be turning lights on and off, trying not to fall asleep. But another thing that you may see when you walk in or out, well, presumably when you walk out of the class, we have an example of a hologram here. Now stop by, take a look. Holograms are actually now pretty common. You know, if you pull out your Visa card, there's a little hologram there in the corner. This one looks a little cooler. It's green. Well, that doesn't make it cooler, but it's much more real. It looks much more real. It's, I don't see what the image is. It's some, some kind of an optical instrument. Anyway, take a look. Yes? Uh-huh. Right. Interesting question. So the question was, how do they, so some percentage of the population is colorblind. We'll actually get back to that, but I can show you the preview of this. This is how people see. This is how human eye works, and we'll discuss that in a little bit more detail, but most people who perceive color have 4 sensors. These cones and rods that sense the that are sensitive to particular wavelengths. When somebody is colorblind, they can be either partially or fully colorblind. One of these may be either inefficient or absent, in which case, you know, some people don't see red, for example. That's a little dangerous when you drive. Maybe a good excuse, but, you know, a little dangerous. Some people may just see, or some animals just see gray. Now, that's the perception side. The rods, these color rods, sense intensity in a particular wavelength, and then we translate it into a color, red, green, or blue. But there's also these rods that just sense the intensity, and so it basically transmits a grayscale picture. So, and then when the colors mix, like here, either in the CYMK color scheme, which is used by printers, or in RGB scheme, which is used by computer screens. And this computer screen isn't perfect. You actually see the middle as a grayish of some kind. My computer screen is better. It's Retina display by Apple, right? I don't own stock. That's not an ad. Transmits white a little bit better. Now, I'm not colorblind. I can actually see these colors. The colorblind person would still see that mixture. It's those colors, all of the intensities mixed together, and then the colorblind person would only observe the intensity of it, kind of with these rods in the grayscale picture. Now, an interesting question is what would happen if only one of these is missing? That's a good question. Usually then you would see presumably you would see a mixture of the colors, but somewhat with some hue. I have a computer projector for my group that's, computer projectors work in the same scheme, RGB. Inside this connector, there are pins that each of them, or a pair of pins transmits a particular color. If one of the pins is broken, for example, then you will be missing one of the colors. That's an interesting exercise or test of how the color blindness would presumably work. A screen is colorblind, and then you would presumably be missing one of the ingredients. Now, there was an interesting question on Piazza. One of our GSIs posted a description of how colors and work, how the sounds work. And then the question, that's Eric, that was posed as to whether you perceive blue the same way as I perceive blue. That's a good question. I have no, hard to say. In other words, do the electrical signals that mean blue to me look exactly identical to electrical signals that mean blue to you? I have no idea. My guess is that not quite. We learn how, the wavelengths are the same, we think. The wavelengths absorbed in your blue cone is the same, but then this wavelength gets converted into some kind of electrical signal that tells your neurons in your brain blue. So does the frequency of those pulses, is that identical for every human or is it not? My guess is probably not. There's probably larger variation. The human brain works at a lower frequencies. There's probably some spread. We just sort of learn to identify particular signals with blue, particular signals with red. That's a good question. Do you see blue the same way as I do? Interesting question for physiology. So hopefully I started answering the question. We'll come back to that. So let's talk about light. There's this cartoon from, I think, a New Yorker about the dual nature of light. Light is something that most of humans, gifted with vision, perceive every day. So this is the first example of a wave, well, maybe the second example of a wave a human ever sees. The first wave one probably perceives are vibrations, either through the ultrasounds that looks at the fetus before it's born, or just the human will probably hear sounds, for example, the heartbeat of his or her mother, and eventually their own. Light is probably the second type of wave that a human will observe when they open their eye. Light is an example of electromagnetic radiation, something that can be transmitted over long distances, something that you can perceive without the need for air to be in the way, without the need for a medium. Last week we talked about waves propagating on a piece of string, waves propagating in the air, waves propagating in the water, earthquakes generated on the surface of the Earth. Those are all examples of vibrations that need material to be transmitted. Electromagnetic waves work differently. They don't need any medium to be transmitted. The electromagnetic waves can propagate easily through the vacuum. In fact, the propagation changes when they encounter materials. So electromagnetic wave is a transfer of energy. It's a transfer of energy over long distances. Distance can be as long as the stars, or even longer, or even further. If you've followed science news, for example, there was a great discovery announced just yesterday. Needs to be confirmed, but what a group of astrophysicists from all over the world, the heads of the collaboration are in Princeton and Harvard and Caltech, but an international group of scientists who look at the echoes of the Big Bang, look at the radiation known to us as the cosmic microwave background radiation, the radio waves that come to us that were created about 100,000 years after the Big Bang and have traveled to us for 14 billion years, are just being detected now. And the scientists look at the tiny fluctuations in that microwave background. Look at the pattern on the sky of the small fluctuations in the intensity of that microwave background that has a typical temperature of about 3 Kelvin, and they look at the microkelvin, or 1 part in a million fluctuations on top of that. And what they see are patterns on the sky of this microwave background that sort of look like circles. This is known as polarization. We'll talk about polarization later, well, on Thursday perhaps, later this week. This polarization imprinted on the pattern of the microwave background in the sky is a sign of another wave, effectively earthquakes, otherwise known but earthquakes, or rather, what's the wave on the surface of the universe? Universe quake? It's the pattern of gravitational waves that were propagating on the surface of the early universe at the time of the creation of this microwave background, about 100,000 times, 100,000 years after the Big Bang. So this pattern of polarization on the microwave background displays or tells us something about how the early universe was developing very soon after the Big Bang. In fact, this pattern of these gravitational waves tells us how the universe developed very early on. It actually is said to be a sign of the process of inflation, which is the exponential blow-up, exponential expansion of the universe right after the Big Bang. Great discovery, but this discovery uses electromagnetic waves. Electromagnetic waves created 14 billion years ago, and have the electromagnetic waves that have traveled to us over the distances of 14 billion light years. Actually, as it turns out, the stuff that emitted is probably a little further. Now, this is an example of electromagnetic radiation that propagates through empty space, scatters maybe a little bit of gas between us and the place where the light was emitted, maybe changes direction a little bit as these electromagnetic waves propagate around massive objects like black holes, and then eventually gets detected by us. Light that we see can be emitted by human-made light sources, can be emitted by our sun, that's about 8 light minutes away from us, or can be emitted by stars that can be anywhere from 4.5-ish, I think, light years away from us, That's Alpha Centauri, the closest star to us, to thousands and more light years. So we don't need a medium between us and the source. Electromagnetic waves and light propagate simply in vacuum. And it's an example of oscillations of electricity and magnetism. It's an example of electric field oscillating in space, creating oscillating magnetic field that in turn creates oscillating electric field, and the process feeds on itself, sustains itself. So that's a wave picture of light. Here I have actually a handy picture of how electromagnetic wave would look in space. It's a combination of electric fields. There's this letter E with a arrow on top of it. That means electric field is a vector. Its electric field is a quantity that has a magnitude and direction. And then there's another field on the side. There's a letter B that stands for magnetic field. So electromagnetic field is a combination of electric fields that oscillate, well, in this case, in the vertical plane, and a magnetic field that oscillates in the horizontal plane, and the whole thing propagating forward with the speed of light of about 300,000 kilometers a second. So that's one picture. And then there's another picture. The other picture is light also, under certain conditions, can be viewed as a stream of particles. And in fact, that's how we would most often would perceive it. Here I push a button on the laser pointer and sends a stream of photons of the green light that correspond to the frequency of 500 nanometers, or the wavelengths of about 500 nanometers or so. So I push the button, a stream of photons exits from the tip of my laser pointer and hits the wall, bounces off of it, and then hits you in the eye. This stream behaves like a bunch of particles. How is that? Well, in particular, if I place, I try not to hit somebody in the eye, if I place, my hand in the way, the stream gets absorbed by my hand, doesn't propagate forward. So it appears to me that these particles travel exactly on a straight line. They can be stopped by an object, and this object would cast a shadow. That's our everyday experience. You go outside, if it's a sunny day like today, there's a shadow. And if you're not a ghost or some other mythical creature, you see your reflection in the mirror, if you're not a vampire. It's sort of directly in front of you. Your shadow is directly behind you from the light source. You cast a shadow. That means light doesn't propagate through you, visible light, right? You're not transparent. At the same time, so this is a so-called geometrical picture of optics, which describes light as something that always travels in a straight line, unless a lens would bend it or a prism would deflect it, travels in a straight line in vacuum, and then an object placed in its way would cast a perfect shadow. That's a particle picture of light. But then there are also conditions where light wouldn't behave that way, would actually exhibit wave properties. In particular, could bend around objects, could interfere, and we'll talk about that later today. Is that, in fact, that electromagnetic waves, and light in particular, has this dual nature. Under certain conditions, they behave like particles. Under certain conditions, they behave like waves. So what we'll discuss today is mostly wave nature of light, in fact, and then we'll talk about particle nature of light on Thursday. The most important parameter, perhaps the most important quantity that describes light, is the speed with which it propagates forward, and that's the highest speed known to man. The speed of light is about 300,000 kilometers a second, or divided by 1.6, 186,000 miles a second, is a large number. Light propagates extremely fast. There's actually a better unit. In fact, some claims that the British imperial system is clearly superior to the standard international system of units. In the international system of units, speed of light is 2.99792.486 kilometers a second. In British international units, the speed of light is, approximately 1 foot per nanosecond. What's a nanosecond? Well, nanosecond actually is a fairly perceivable, not by a human, but by a fairly perceivable unit by electronic devices. Your cell phone, if it's a smart cell phone, has an internal oscillator there that flips beats roughly once a nanosecond. It runs at this is Samsung. It has, I think, a 1.5 gigahertz processor in it. This is an old generation, old as in 2 years ago. Galaxy 3. It has a internal oscillator which runs at a 1.5 gigahertz frequency. And if you're buying a new computer or buying a new device, you usually want to find the latest and greatest, the speediest processor, which has the highest frequency. We'll discuss whether that's always appropriate later today and on Thursday. But what these units mean is that inside the processor there's some piece of electronics that flips, that oscillates, that runs the clock, the internal clocking mechanisms of this electronic circuit, and it flips slightly faster than once per 1 billionth of a second, once per nanosecond. So electronic devices nowadays can easily produce oscillations at the frequency of 1 nanosecond, or with the period of 1 nanosecond, or even faster. Some electronic circuits can react to particles of light within a few to 10 femtoseconds, which is another 1,000 times, or rather femtoseconds is another 1 million times shorter than a nanosecond. It goes nanosecond, picosecond, femtosecond. So 1 nanosecond is a relatively large unit, and in this 1 nanosecond, 1 billionth of a second, light travels this much. So speed of light for scientists, actually, somehow physicists don't often use this unit. For an experimental physicist, speed of light is 1 foot per nanosecond. So I can say that this is a nanosecond, this is 2, this is 3, and that's actually a convenient unit. You can take a piece of wire, and that's how we actually measure time often. You take a piece of wire the length of a foot, you plug it into a source of electromagnetic oscillations. These oscillations will come out on the other end exactly a nanosecond later, if the length is a foot. Well, it has to be a fiber cable, fiber optic cable. If you take a normal coaxial cable that you find in your, stuff like this, that you find in your cable TV, or the stuff that brings cable TV signals to you, speed of light in those cables is a little bit slower. There's some index of refraction inside that we'll discuss. And the speed of light, typically about 60%, speed of electromagnetic waves is typically about 60% of the speed of light in a cable. So the cable company is sending you signals from maybe miles away from the retransmitting station, and they're coming to you at the speed of about 60% of the speed of light. We now understand the speed of light, the actual full number of 300,000 kilometers a second, as the maximum achievable speed limit, as the absolute highest speed any massive object can potentially achieve. There was a story about this a couple of years ago, which you may also have read. So in the news, there was an experiment in Italy in a lab that I often go to perform other experiments. It's a Gran Sasso National Lab underground, about 2 hours east of Rome. They had a large detector that was looking at very light, very low interaction rate particles called neutrinos. We'll talk about that towards the end. Those neutrinos were produced about 2,000 kilometers away at another national laboratory in Switzerland called CERN. And I tried to measure the time delay between the creation of the particles and the detection of the particles. So at CERN, they had a clock. That clock would count time very quickly in units of nanoseconds. So they were oscillating at about 1 billion times a second. And they would record when the particles were produced there. And then the scientists in Italy would record when the stream of neutrinos, sort of like this slight pulse, would get to them. And they would compare the times sometime later. And as it turns out, there was an error in that calculation, while the error was actually in the hardware that the Italians used. Some piece of cable was not plugged in correctly, and that created a time delay of about 60 nanoseconds, 60 billions of a second. So something like 60 feet were lost. And so for a while before they discovered this hardware problem, there was a great hoopla about this result. It's looked for a while as if neutrinos, these very light particles, were traveling slightly faster than the speed of light. If that turned out to be true, that would have been a great breakthrough and discovery. It turned out to be false. But science does make mistakes sometimes. What we try to do is to then look for them, correct them, and that's part of the scientific process. So in that case, the team has looked very carefully, took them a few months, and then they found an unplugged cable. Slightly embarrassing, but in the end, the right process. So what we understand now is that Einstein postulated, and all of our observations, including this one, are consistent with the fact that any particle that we can create in a laboratory or can observe travels slower than the speed of light, or rather no faster than the speed of light. And if you observe something that's traveling exactly at the speed of light, those particles have no mass, like the particles that stream from the end of my laser pointer, known as photons. Now, when light propagates through some materials, or some mediums, through air or through water, it typically gets delayed a little bit. And it gets delayed because it has to interact with the molecules in that material. Those molecules absorb a bit of electromagnetic radiation and reabsorb it, or they slow down the propagation. And in that case, the speed of light in the material is lower than the speed of light in vacuum, so slightly smaller than c. And so as I said, the electromagnetic pulses that carry your TV signal from a cable TV station propagate to you a little bit slower, at about 60 to 70% of the speed of light. So again, here's the picture of how the electromagnetic wave looks. It's a series of oscillations of electric and magnetic fields, sort of like this. Electromagnetic wave is known as a transverse wave. What it means is that the oscillations of electric and magnetic fields happen in the direction that's perpendicular to the direction of the wave propagation. So if I send my laser pointer, so if you imagine that this is the picture of electric field produced by my laser pointer, and I send it that way, the wave propagates forward like this, and it consists of electric oscillations, let's say up and down in this plane, and magnetic oscillations that oscillate in the direction always perpendicular to electric field. And James Maxwell in the 19th century has demonstrated through a set of equations known as Maxwell's equations now, not surprisingly, that when you have an oscillating electric field, that oscillating electric field can create an oscillating magnetic field. When you have an oscillating magnetic field, it creates an oscillating electric field. That last part is known as a Faraday effect. This is how the transformers work. If you remember, in the transformers, you can send an oscillating electrical current that produces an oscillating magnetic field, and then on some other side of the transformer, you can pick up the signal through an oscillation of conversion of electric field into, or rather magnetic field into electrical current. Electromagnetic field waves work exactly the same way, but they don't require even wires. Oscillating electric field produces magnetic field and vice versa, and the self-sustaining oscillations keeps propagating forward. The wave has the wave speed. That's the speed of light. And then the pattern of these oscillations repeats in space periodically. There are maxima. There are places where the field is large, like this. And there are places where the field is small. And then there are places where the field is large again. The distance between the two peaks of the electric field, we understand, is known as the wavelengths, is the characteristic size over which the field changes by 100%. And this pattern keeps propagating in space with the speed of light. So we can characterize the electromagnetic waves by this distance between the two peaks in the intensity. This is known as the wavelengths. So the electromagnetic waves then can have any wavelengths. The actual wavelengths depends on what source has produced those oscillations in the first place. It depends on the electromagnetic waves are produced by some vibration of charges, of electrical charges. And so depending on which frequency those charges vibrate, the electromagnetic frequency of wavelengths will depend on that source. So here on this graph, what's shown on this graph is are the typical frequencies. And then by multiplying them by, or dividing them rather by wavelengths, or by rather speed of light, taking the speed of light, dividing the speed of light by frequency, you can convert frequency to wavelengths. So the electromagnetic waves also correspond to a particular distance scale in space. And the range can vary from long wavelengths produced by radio antennas. For example, when you listen to AM radio, you set your dial to some number on your AM dial. The numbers are typically in the hundreds to thousands. So, you know, this morning I was listening to KCBS, that's 7:40 a.m., I think, yes. 7:40 a.m. 740 is the frequency of oscillations in thousands of hertz. 740 kilohertz, here somewhere, is the frequency of radio waves. If you change your radio to FM, you pick up signals at a higher frequency, at the frequency here of about 100 megahertz, 100 million oscillations a second. So you change your station to 98.5 KFOX, that's the classic rock station, also carries San Jose Sharks games in the evening. That number, 98.5, is the frequency of the oscillations at the radio station in San Jose somewhere that has the oscillator that sends pulses 98.5 million times a second. So that frequency corresponds to the frequency of oscillations that then can be translated into the wavelengths of light that is measured in meters. Remember, speed of light is 1 foot per nanosecond. And let me erase this. Last week I wrote you a formula for, no chalk. There's a relationship between the frequency of vibrations and the speed of light, and the speed of vibration. Frequency and wavelengths are related by the following formula. You take the frequency, multiply it by wavelengths, and you get the speed of light. So wavelengths and the frequency are reciprocal of each other, inversely proportional to each other. So I can rewrite this equation and say wavelengths is the speed of light over frequency. And the speed of light is 1 foot per billionth of a second, or 1 foot per frequency of 1 gigahertz. So speed of light is 1 foot per nanosecond, or 1 foot per gigahertz. So if a frequency is 1 billionth of a hertz, a gigahertz, the wavelength is a foot. If the frequency of the FM station is 100 million hertz, is about 10 times smaller, the wavelength is 10 times larger. So the wavelengths of this 98.5 kFox radio station is about 10 feet. The wavelengths of the AM station is another 100 times longer than that, 1,000 feet. What does this mean? Well, it means that when these electromagnetic waves propagate through space, if they encounter objects that are of roughly the same size as the wavelengths, they will behave like waves. In particular, they can move around objects, exhibiting the process known as diffraction that we'll show you. And those objects will not cast a perfect geometric shadow. So if the wavelength is shorter than the size of the object, the wave behaves like more or less like particles, and objects cast perfect geometric shadows. If the wavelength is larger than the size of the object, the wave can move around it. And so the electromagnetic wave, including light, will behave either as a set of particles or a set of waves, depending on really the sizes of objects that are in the way. AM waves, being long, thousands of feet, can move around large buildings, can diffract around large buildings, which is why you can typically listen to AM radio over very long distances. At some point, I was driving. I think I was in Tahoe somewhere, turned the dial, was looking for a Sharks game on AM dial. FM doesn't, there's no line of sight between Tahoe and San Jose. I couldn't get the FM station. I was looking for AM dial, and I picked up a signal from Calgary. Calgary, Alberta in Canada, that's what, 2,000, 3,000 kilometers away, miles, units. Clearly not in the line of sight. The long AM waves could bend around the curvature of the Earth, propagate towards my radio antenna. They can move around, again, long buildings. On the other hand, if you drive into a tunnel, AM radio waves lose reception. You start hearing static, and the reason for this is that that long wavelength cannot fit inside the tunnel that's less than 1,000 feet across. So you start getting slower and weaker signals. FM signals have wavelengths of tens of feet. They can fit inside the tunnel. You usually don't lose reception very much for the FM radio. As you increase the frequency, the wavelength decreases. And so the wavelengths of your microwave, or the wavelengths of radiation that carries cell phone signals, is about a foot. Corresponds to a frequency, well, slightly about a third of a foot. The microwaves typically operate at a frequency of 2.4 gigahertz, 2.4 billion billionths of a second. The cell phones transmit typically at a frequency of 1.7, 1.8 gigahertz. That's if it's LTE signals, digital signals. So the wavelengths for a cell phone is about half a foot. That's about this much, 6 inches. Wavelengths of your microwave radiation is a little bit shorter than As you increase frequency, the wavelength decreases. Infrared radiation corresponds to wavelengths of microns or so, tens of microns. As you increase the frequency yet more, we get into the visible light spectrum that has the wavelengths of a fraction of a micron, or somewhere from about 0.3, 3/10 of a micron, to about a micron. As you reduce the wavelengths yet again, increase the frequency, we move into the ultraviolet region, and then to X-rays and the gamma rays. And so you can view various, so as I said, long wave signals from long wave radio can diffract around, can move around objects. What it means is that they don't notice them very well. They sort of, the intensity of AM radio doesn't change very much as they diffract around objects. So it's very difficult if you're, building a radar to look at, say, image tall buildings. You probably wouldn't use wavelengths of thousands of feet, because though that radiation would scatter, well, rather diffract around objects, and you won't notice them. So if you want to image, if you want to look at objects that are of a certain size, you typically would pick up radiation of the wavelengths that's smaller than those objects, so that those objects can actually cast a shadow, and you can deduce that the objects were in the way by observing the intensity variation, by observing shadows. So if you're trying to image things like cells, you would typically use wavelengths that are of the same size as the cell or smaller, so that would be visible light. If you're trying to image something of the size of the molecules, you would typically need to go to shorter wavelengths and higher frequencies. And if you want to image atoms or nuclei, then you need to go to wavelengths that correspond to X-rays and the gamma rays. And that again comes from the wave nature of electromagnetic radiation. Now you may ask yourself, our visible light corresponds to a fairly narrow range in this, on this chart of somewhere between 300 nanometers or 3/10 of a micron to about a micron. Why is that? Why is our eyes so narrow in the perception, in the frequency range? Why don't we behave like that predator from some Schwarzenegger movie that sees in the infrared? Well, the reason for this is there are two reasons for this. We actually could have developed, as it turns out, as a predator, but our perception depths and the contrast probably wouldn't be as good. And also, some things would look a little bit hazier or fuzzier to us if we were to see in the infrared. This is the spectrum of electromagnetic radiation in the visible and the infrared in the atmosphere. This is roughly, if you plot intensity of radiation as a function of wavelengths here, you would see two bands in the spectrum. One corresponds to the visible light, and that corresponds to the frequencies, or rather wavelengths of, as I said, third of a micron to about a micron. Most of that intensity corresponds to the temperature of our sun. We happen to live near a star that has a surface temperature of about 6,000 Kelvin. And that star emits radiation in the visible range, luckily for us. This is the picture of the spectral intensity, the intensity of light as a function of wavelengths for different temperatures. As it turns out, any object that is at non-zero temperature emits some kind of light, emits some kind of the electromagnetic waves. Some of that light is visible, corresponds to this very narrow range in the frequency spectrum. Some of this light is invisible. And we'll talk much more about this when you guys come back after spring break, but any object that's heated up emits light of some kind. And so there's a relationship between the temperature and the wavelengths. This relationship is such as that the hotter the object is, the shorter the wavelengths that it will radiate. So we happen to live near a star that's relatively warm. It's not the hottest star, but it's also not the coldest star. It's sort of like the, it's just right. I'm trying, what's the, I'm going senile, and I'm trying to remember what the girl's name was that was occupying Goldilocks, right? That was occupying poor bears' houses. So the frequency is just right for us, Goldilocks, yes. This frequency is just right for us. Well, but it's also just turned out that our eyes have developed over the evolutionary period of billions of years to actually pick up frequency in exactly that range. Not surprisingly, because, well, we developed here on Earth, which is near the star that's radiating with the typical wavelengths of around half of a micron. As it also turns out, again, luckily for our development as the species, that this frequency also corresponds to the frequency range where air is transparent, right? I see you guys pretty clearly. Light that bounces off of you and then hits me in the eyeball doesn't get absorbed by air. If you lived, let's say, I don't know, if our air was filled with silicon, I don't know, if you ever saw silicon chips, right, you can open them up, they are not transparent, they're blackish. If our air was filled with silicon, I don't know why it would be, but say our atmosphere was a silicon atmosphere, I wouldn't see you. Light would be absorbed. Again, perhaps luckily for us, the atmosphere is transparent and exactly the same frequency range as where our star has the peak intensity, so we can develop optical instruments that are sensitive to exactly that range. If the air wasn't transparent in this range, it may have been transparent in this infrared range, and maybe we would have developed vision in the infrared. So perhaps that predator species developed on a planet which had atmosphere that wasn't transparent and visible, and the vision developed in the infrared. Of course, these wavelengths are about 10 times longer, and therefore the sharpness of the image you can get in this wavelengths is about 10 times worse, at least the highest sharpness. All right, so let's come back to this picture. I actually wanted first to show you the two facts. The fact that every warm object radiates. If you don't believe me, here's the demonstration. Well, I'll let this strip piece of metal warm up. So here's the question for you. I have this strip. Here's a piece of metal. It has white marks painted on it. It also has clearly darker regions. What do you think will radiate better? The white spots or the dark spots? What will produce high intensity? Any clues? It's not a quiz yet. There are only two possible answers. Well, there are three possible answers. There are many possible answers. There are two answers that are acceptable in this case. Well, white will radiate more, and the other one is black will radiate more. Well, the third one is that they will radiate equally. So what do you think radiates? Which color do you think radiates more, black or white? Let's find out. Can we turn the lights off, please? Okay, this isn't hot enough yet, and we are not yet in the dark. We should probably kill the screen completely. Oh, and I have various light sources that I probably need to turn off as well. That, and how's this? Do you start seeing red? Yeah. Should start seeing this strip. The strip is starting to glow. And as it warms up, the glow becomes redder and redder, and well, if I were to heat it up even more, it would eventually, the red color will become yellowish, and then it will become greenish, and then it will become bluish. Now, hopefully I'm remembering my colors right. But at this point, it's red. The temperature is obviously not as hot as the sun's surface. It's not at 600,000 Kelvin. So what you see is a slightly red color. It's actually primarily radiates in the infrared. But you see that the points with highest brightness, actually the places that, wider regions. Can you turn the lights on, please? That correspond to darker spots. So black actually radiates better than white. If we can turn on back on the screen. So there's, it's one of the reasons why the law that I've just described to you is known as a black body radiation law. As it turns out, all objects radiate. In fact, the black radiates best. White is a good reflector, but not a good absorber. Light reflects off of the white surfaces, reflects all colors equally. If your piece of clothing looks white, it means that it reflects all wavelengths roughly equally, and all of these wavelengths mix in your perceptors and correspond to a white color mixture. White object doesn't absorb very well. And the black body law of radiation says that whatever, or that the efficiency to absorb is exactly the same as the efficiency to emit at the same wavelength. So objects that absorb very well also emit very well. And what absorbs better than black? So black body radiates perfectly, and the radiation depends on the temperature of the body. In fact, black bodies only look black in the visible spectrum. They look pretty bright. They may look pretty bright in the infrared. All of you radiate, and we'll talk much more about this after we come back from the spring break. I think the book says something like that all of you are as bright as a light bulb. Well, you're actually brighter than that. All of you are figuratively bright, but you also are literally bright. You actually radiate roughly a kilowatt of power, a little more than that. As it turns out, you also absorb a lot. Fortunately, we live in an environment where the temperature is just a little bit cooler than our body temperature. My body temperature is 36 degrees C, or roughly 310 Kelvin. Your body temperature is about the same. I cannot claim I'm hotter than you. The power that you emit is proportional to the force power of absolute temperature measured in Kelvin. So if your temperature is about 310 Kelvin, you radiate in the amount proportional to that. The environment around you sits at slightly lower temperature typically, You know, your temperature is 36 degrees, you know, the room temperature is about 20 degrees C. There's about a 15-degree difference. That 15-degree difference in Kelvin corresponds to roughly 5%. Is that true? 15 over 300 is roughly 5%. So the objects that are all around you radiate less per unit area by about 20%. That's 5% to the, or 1.05 to the fifth power is the difference per unit area of how much you radiate versus how much you would absorb from the surrounding objects. And then, you know, closing helps to keep some of your radiation in. So typically the difference between how much you radiate versus how much you absorb is about 100 watts. And that you have to recover by eating, by processing food. But if you were in space, you would radiate much quicker. There wouldn't be any objects radiating towards you. You would radiate about 1 kilowatt. So you're as bright as an iron in space, but here on Earth, you look to everybody as bright as a 100-watt light bulb. Now, as I mentioned, the human eyes have developed over the billions of years of evolution to see in a particular spectrum. We see visible light rather than infrared. And as we were talking about in the beginning, the human eye has several important features to it. We have the iris that's iris pupil. Pupils dilate, so that's a pupil. Iris is the sort of what makes eyes pretty. I'm not sure what other functions there is physiologically, but well, presumably it has some, you know, evolutionary feature, right? You know, you fall in love by gazing at somebody's eyes. Oh, that's important evolutionary. But the pupil is the first optical element in your eye. Oh, actually, it's the second. Optical element in your eye is the cornea, is the surface that separates your eyeball from the environment. Light coming in bounces off of it, passes through the pupil, through the image aperture. Size of the pupil can change depending on the size of the amount of the light striking your eye. Your pupils dilate. That is, increase in size when you're in the dark room or when you're excited, and shrink when the light is bright. Then the light is imaged on this lens that changes the sharpness of the image on these photoreceptors on the back of your eyeball called retina. We'll talk about how the optics works on Thursday. From the color perception point of view, the back of your eyeball is filled with the photographic receptors, photoreceptors, each of them sensitive to a particular frequency of electromagnetic radiation. They're known as cones and rods. Rods provide you with just the measurement of intensity, so they produce a grayscale image. And then the cones filter light at specific colors, specific frequencies in red, green, and blue, forming the standard RGB color map. So what this plot shows is how the relative intensity, or relative perception rather, of each of these photographic elements depends on frequency. So the blue rods are sensitive to the electromagnetic radiation in the range of about 400 to 500 nanometers. That's what we call blue. Somebody else may call it something else, you know, depending on the language and the species. Our green receptors sense wavelengths between 450 roughly and 650 nanometers. And then the red is shifted a little further to the right still to the the peak intensity that peaks around 600 nanometers. And this matches quite well with the overall luminosity produced by our sun and also filtered out by the atmosphere. Again, the mixture of these colors can look to us as a color that's in between 2 or 3 primary colors, and the mixture of all 3 looks to us as white. Here are the examples of this. If you, right, the screen again isn't perfect. So I have a bright lamp. And a screen. There you go. So this looks greenish, right? You guys on that side can see green. You guys on this side can see green. I can change the filters here. Let's see, how do I do that? Ah, there you go. Open this one, open that one, open this one. So if I set up all filters, there will be areas. Oh, okay, blue isn't as bright on the screen as the rest. But in the areas which overlap, you'll see colors that are in the intermediate state. Yes. In the region where all colors overlap, you would typically see white. Now, this is the, can we switch back to the screen? This is the color scheme that corresponds to different light intensities that are, or different colors that are emitted at specific frequency and wavelength ranges. Can you turn the screen back on, please? Can you turn the screen back on, please? The other way to transmit color information, or rather to encode particular color information, is not to transmit a specific frequency, but rather absorb a specific frequency. So this corresponds to the CA-CYMK color scheme used by color printers, which produce images on a piece of paper in ink that is designed to absorb specific wavelengths. Do you have a problem with the projector? Projector seems to be on. Ah, okay. Well, I can talk in the meantime. We'll actually, another demonstration here that your perception depends on the wavelengths and the visible light is a range of colors. You can see, oh, there you go. Thank you. So another demonstration that the visible light is spread into multiple colors. You can see on a rainy day when you see rainbows. Here I actually have a rainbow maker. So I can split the different colors into particular frequency or wavelength ranges. When you see the rainbow, those colors are split by raindrops that act as prisms that deflect different colors of the light by different angles. We'll talk about this on Thursday. You can also do the same thing by an artificial device called the diffraction grating that will deflect the light of different colors at different angles. So if I start with the visible light, rather white light. So on this side, I mean, if you look at this lamp, it looks white to you. This light passes through a number of optical elements that focus it on a diffraction grating, and then this diffraction grating splits the colors on the screen. You can see it. You can see it because the intensity isn't very high. Can we turn the lights off, please, for a second? You'll see here on the screen different color spots. Red on this side, green on this side, blue and violet on that side. So this diffraction grating works exactly like the prism or a droplet of water after the rain. It splits light into different colors by deflecting each wavelength by a different angle. Red is deflected most, and violet is deflected least, so it shows up a little bit further on the screen. Now I can actually change the temperature of my light bulb here by changing, increasing or decreasing the current that I send through this light, and you actually see different colors disappear one at a time. I'm running this light pretty hot now, this light bulb pretty hot now. If I decrease its temperature, you'll start seeing blues disappear first, and then the greens disappear, but the red still stays. And then the reds will disappear completely, and the light turns off, almost. As I increase the current, and I increase the temperature of the light, reds will show up first, then the greens will show up, and then the blues. Again, this corresponds to the fact that the emission spectrum of light depends on temperature. The higher the temperature, the smaller, shorter the wavelength is, according to this graph. And so if you move the temperature around, the peak of the spectrum moves from infrared to red to yellow to green and then to blue. And again, to perceive the color or to display the colors, you can either emit at specific frequencies. So liquid crystal displays, computer screens emit lights at different colors. Then the mixture of the lights of all colors represents white. On the other hand, if you look at the reflected light, the easiest way is to transmit color information is to absorb light at certain frequencies and only re-emit others. So this is known as CYMK color scheme, where this blob absorbs everything but yellow. This blob absorbs everything but magenta. And this blob absorbs everything but cyan. And of course, the region where all four overlap absorbs everything and looks black to us. So color printers then are designed for this with this color scheme, where the color printers have 3 color inks, each absorbing in a particular frequency band, plus black. Because it would be wasteful to produce black ink by putting droplets of ink of all 3 colors, and so black is then transmitted, or rather applied separately as a extra ink cartridge, since most of you print in black anyway. So now these patterns describe the wavelengths features of light. Of course, a much more interesting features of electromagnetic radiation is the fact that it does behave like waves. In particular, we talked about this last week, waves don't always go on straight lines. Waves sometimes exhibit behavior known as interference. You've heard beating sound from the audible sounds. Those are examples of wave behavior of various waves, including electromagnetic waves. Here's an example of interference that you can observe on the surface of the water. We talked about this last week, that sources on, say, 2 boats on the surface of the water can produce waves that radiate outwards from the boat, producing these circle-like patterns. And then the places where those waves overlap can produce regions where oscillations add up coherently in phase and reinforce each other, producing large amplitudes. And there will be regions in space where the waves distract, where intensities are subtracted from each other, cancel each other, and in those regions you produce quiet patterns, you produce troughs of oscillations. Exactly the same thing happens with visible light. Visible light can, two sources of light of the same frequency, of the same wavelengths, can either add up constructively and reinforce each other, or can add up destructively and cancel each other. The easiest way to see this is when you look at an oil spill, or when you look at a soap bubble. If you look at a soap bubble produces very cute rainbow colors. The reason that this happens is that when you look at the surface of a soap bubble, you actually see light from two different sources. See the light that scatters off a surface of the bubble. Surface of the bubble has some thickness to it. And so light getting into your eyeball, so here's your eyeball, light can reflect off of this surface and get into your eyeball. And light can reflect off of the inside surface of the bubble and get into your eyeball. And those two waves will either reinforce each other or they will cancel each other out. And so if a particular wavelength of light corresponds to a constructive interference where these two waves add up in phase, add up in such a way that they increase each other's intensity, you'll see a bright spot. And if a wavelength is such that this extra path length will produce a cancellation of the wave that's reflected from the inside surface, you'll see a dark spot. So what you see is the rainbow pattern because at some angles at which you look at the bubble, soap bubble, or an oil spill on the surface of the water, some particular angle you see an enhancement, and that particular angle will correspond to a bright color, and some angles you see a darker regions. And I'm not sure if I can see this on the screen. Oh yeah, if you can. Can we go back to the projector? I have some oil, or rather soap, on the surface of the water on the camera. And eventually it will come up. No? Technical difficulties? Let's try it again. There you go. You sort of see streaks here, because the color, maybe turn the lights off, and maybe the color will come out a little better. No? Well, I'll give up for now. Come back after the, when we finish. You'll see the surface of the water that looks like a range of red, green, and blue colors at different angles, and it corresponds to this interference effect for light reflected from one side of an all slick to another. Another wave phenomenon that is important for visible light, as well as for sounds and also waves on the surface, is called diffraction. And this diffraction is the phenomenon that describes waves propagating through a small aperture. When the aperture is roughly of the same size as the wavelengths of the wave, you see a spread in the angle of the waveform. The waves that initially come at this aperture, let's say in the perpendicular direction, appear to spread out and produce a circular wavefronts. The spread in the size of the waveform, the angular size, or rather the angular size of the waveform, depends on the wavelengths and the size of the aperture. So the physical size of the waveform in meters grows with distance. It depends on the distance from the aperture to where you observe the wave, divided by the size of the aperture multiplied by the wavelengths. So if the wavelengths is comparable to the size of the aperture, this ratio, wavelengths over the aperture diameter, is large, is of order 1 in radial degrees, radian units, or in, corresponds to a large spread of the waveform of the order of 60 or maybe even 90 degrees. So the wavefront that comes at an aperture spreads out into a larger angular distribution. If the wavelength is very small compared to the size of the aperture, then the spread of angles is small, and the wave looks still fairly collimated. Here, the wave coming out of the tip of the laser pointer doesn't spread that much and produces a spot that's well collimated and focused. At the same time, if the wavelengths were short compared to the size of the aperture, the wave would spread out more. Sound waves correspond to wavelengths of the order of meters. So if I stand in front of the opening that has about the same size as the size of the wavelength, say the door, the sound waves would propagate out of the door and spread out. So somebody standing outside of the door and not in direct line sight would be able to hear, would be able to see, to hear, rather perceive sound intensity. At the same time, the size of the door is much larger than wavelengths of visible light. So the door, or rather the outside of the door, casts the perfect shadow. Visible light does not penetrate through the outside of the door, only penetrates through the opening, and in particular, light doesn't bend around the corners. Despite what you see sometimes in the late night infomercials, at some point about a few years ago, I turned on, I work late at night sometimes, I turn on the TV, and there's this infomercial about a perfect laser level. You mount it on the wall, you push the button, and it draws a perfect straight line. That's quite possible. But that straight line bends around corners so that you can hang the picture somewhere around the corner. I'm not exactly sure how many units they sold. I think this infomercial disappeared from the TV screens about a month later, presumably after consumer complaints. But light generally doesn't do that, right? If I push a laser pointer button and aim it at the edge of the door, you'll probably not see a large intensity around the corner. But if I send this light through an object that has the size comparable to the wavelengths of light, then we'll see diffractive effects. So I'll stop here. We'll demonstrate diffractive effects with light with devices, laser devices, on Thursday. As you come out, stop by this hologram demonstration. It's an example of a device that uses interference enhancement of light at specific frequencies to encode depth perception. So take a look.